I'm Calvin Pritchard, and I work at computational modeling for the social and ecological sciences as a software developer and data analyst. Today, I'm going to be talking about the Megadapt project. The Megadapt project's purpose is to explore the vulnerability of megacities to ponding and flooding events from storm surge. Vulnerability exploration involved collecting data about climate, flooding, ponding, and infrastructure, determining the impact of different infrastructure management policies on ponding and flooding event frequency and strength, consulting with residents, infrastructure managers, and other stakeholders to determine priorities on public and private freshwater and stormwater infrastructure, and modeling infrastructure management policies and environment to explore policy impact over the next 50 years. The Megadapt model is composed of an infrastructure planner and census blocks with demographic, preference, environment, and infrastructure data. Census blocks have environmental information and make decisions about how much private, potable, and stormwater infrastructure to invest in. Potable water investment reduces water scarcity, and stormwater infrastructure investment reduces the impact of floods. Census blocks make private infrastructure investment decisions based on a resident mental model. City managers make potable and stormwater investment decisions based on their mental model. Investments increase capacity, flow rate, and the proportion of the population served. Flooding and ponding event frequency is influenced by the stormwater system capacity as well as precipitation and runoff. Health is influenced by potable water access as well as ponding and flooding frequencies. Updates to public and private infrastructure change census block state, which in turn influences resident and city manager infrastructure decisions in the next time period. When CoMSES began involvement in the Megadapt project, a lot of modeling work had already been done. A theoretical model had been implemented in NetLogo, and gradual conversion of the entire model to R was underway. Why? Because the R to NetLogo bridge was too brittle and some functionality from R was needed. The NetLogo implementation was also too slow. CoMSES was contracted to make the model reusable and runnable for different scenarios in study areas. On the left shows what many R projects looked like. A bundle of unstructured files of many types living in one directory. A better approach than developing a project structure on your own is to follow the package layout and create a package. Megadapt was turned into an R package. Why is an R package better? Packages have standard file locations that make code easier to read. They simplify installation from description files and allow version pinning. They have scaffolding for running model component tests. They force minimum modularity and documentation standards. And they also ease documentation creation and distribution by having manuals and vignettes part of the build process. Code in the Megadapt R package follows particular interfaces and code organization principles. R files are organized around model components. There is one file for every model component. Components have an interface for initialization, serialization, and deserialization, which eases parameterizing the Megadapt model. Components are also either simple functions or follow the discrete time state specification. The discrete time state system specification is a formalism with two methods, an output function and a transition function. The output function takes the current state and returns an output. The transition function takes the current state and an input and returns a new state. Time in DTSS advances at a constant rate. In the Megadapt model, this rate is 1 year. To simulate the Megadapt model, a simulator has to be chosen. The graph in the current slide shows one complete cycle of a simulation algorithm inspired by the coupled discrete time state system specification coordinator outlined in the theory of modeling and simulation. Nodes in the graph can be thought of as components. The oblong study data node can be thought of as a memory unit. The output function returns the current state, and the transition function sets the state with the current input value. Rectangular nodes are stateless, model-specific components. Circular nodes are generic operation components. The apply circular nodes update a study data set with a provided patch. The join node combines all incoming patches together by census block ID. Edge numbers represent the order that messages are sent between components within a simulation step. First, the output functions of all stateful components are called. Since the study data component is the only stateful component, its output function is called and messages are sent to all study data component subscribers. Then, all stateless functional components are called as soon as their input messages are available. This means that functional components must wait for one another. The flooding and ponding model components, for instance, must wait for apply to emit an updated study dataset. At step 6, a new study dataset is sent to the study data component. The study data component's transition function is then called, and the study data component's state is fully replaced with a new state. Time is then incremented 1 year. And that is the end of the simulation step. Megadapt model initialization is completely separate from the simulation process. Initialization is handled by delegating to its subcomponents. The municipal investment, water scarcity, residential investment, climate, ponding, and flooding subcomponents all have their own initialization functions. These initialization functions are called in order of their data dependencies, so that the climate model's initialization procedure is called to create its column data on the study data before the ponding and flooding subcomponent initialization functions are called. Many people at Landsys, ASU, and CoMSES work together to create the Megadapter package and its associated visualizations and analyses. So far, we have visualized model outcomes for stakeholders to explore the impact of policy and environmental conditions, analyzed the importance and impact of variables such as budget, infrastructure management strategy, and infrastructure depreciation on the vulnerability of residents, improved the build environment and runtime to simplify installation and running the model on high-performance computing, performed variance-based sensitivity analysis of primary model parameters, and deployed the Megadapter package using containerization software such as Singularity on high-performance computing at ASU and UNAM. Let's take a look at some of the visualizations. Some of the visualizations were diagnostics. This plot shows the number of infrastructure investment units by census block for a short 5-year model run. It was made to determine if infrastructure investments were being made in the expected places. This visualization application shows water scarcity and flooding vulnerability values by varying the budget and climate scenario. Here are the results of the sensitivity analysis. It shows that changes to the budget level explain most of the variation in mean water vulnerability outcomes. The next scatter plots on this and the following slides show water scarcity vulnerability and flooding vulnerability, respectively, as categories on the y-axis compared with different budget values on the x-axis ranging from low to high. Both plots show that some vulnerability persists even at high budget levels. The associated maps display the index values at fixed budget values. After working on the Megadapt project, I have a few thoughts about takeaways and next steps for CoMSES and the community. My main takeaways are that R has tutorials on containerizing scripts and packages, but is missing project setup tooling and templates for containerization. Support for flexible model parameterization was necessary to be able to run all the needed model configurations. At the beginning of the project, we had a simpler model parameterization set, but this resulted in not being able to control many parameters. And start with small, concrete examples and incorporate data visualization and visual feedback as soon as possible, because the model runs much faster with only a few census blocks, and small examples are much easier to troubleshoot and test. Possible next steps for CoMSES and the open modeling community include developing community standards and enabling users to easily add containerization to their new and existing R packages and projects, taking the use this R package as inspiration, and creating a guide for building flexible model component parameterizations, organizing model components, and adopting different modeling formalisms. Thank you for listening to my presentation. I'll see you in the discussion forums.